Let's take a look at finding the derivative of functions involving trigonometric functions, but also require the use of the chain rule. So our first function here is g of x equals -2 times cosine of 4x. So as we look at this function, we can notice that 4x is the argument of the cosine function. So as we apply the derivative to this particular function, when we deal with the cosine of 4x, we will need to be using the chain rule. So let's go ahead and get started. So g prime of x is equal to, and now because of this coefficient of -2, we're going to go ahead and apply the constant multiple rule. And so this is -2 times the derivative of the cosine of 4x. And now when we start to take that derivative of cosine, so we'll have -2. Now the derivative of the cosine function is negative sine. So we're going to have negative sine of my argument times the derivative of that argument. And my original argument was 4x. So then we are now ready to find that derivative of that argument, or the derivative of 4x. And we have a negative of a negative, so we're going to say that's positive sine of 4x times the derivative of 4x, which is 4. And now we can go ahead and multiply our 2 and our 4, and so we end up with g prime of x equaling 2 times 4 is 8 sine of 4x. So there we have the derivative of g of x. Now let's take a look at our second function here. We have y equals the sine of the square root of x. So notice that the sine function has an argument that is square root of x. Plus, then now we have a square root function whose argument is sine of x. And since there are radical components to this function, we will need to rewrite the function using exponent form. So we would rewrite this as sine of, now the argument of the sine function is square root of x. So that's x to the 1/2 power plus, and now we have a square root function. So we're going to have something to the 1/2 power, and the argument of that square root function is sine of x. So what we're taking the derivative of is y equals sine of x to the 1/2 power plus the square root of, or the 1/2 power of, sine of x. So now we're ready to go ahead and start finding that derivative. So dy dx is equal to the derivative of sine of x to the 1/2 power plus the derivative with respect to x of the 1/2 power, or the square root of sine of x. So sine of the quantity sine of x to the 1/2 power. So now let's go ahead and apply the chain rule to find the derivative of those two terms. So we have dy dx equals, now the derivative of the sine function is the cosine function. So we're going to have cosine of our argument times the derivative of our argument. And our argument was x to the 1/2. So we're going to have cosine of x to the 1/2 times the derivative of x to the 1/2. Plus, Now, in our second term, that outer function is the square root function, and our argument is sine of x. So dealing with the square root function first, we're going to have 1/2 times, leave the argument alone, and then 1/2 minus 1 gives me a negative 1/2 power, times the derivative of our argument. And our argument was sine of x. So continuing on, to finish out this chain rule, we have dy dx equals cosine of x to the 1/2 power times the derivative of x to the 1/2. That would be 1/2 x to the negative 1/2. Remember, this exponent for my x is 1/2 minus 1, plus 1/2 times sine of x to the negative 1/2 power times the derivative of the sine function, which is cosine of x. At this point, we are finished finding the derivative, and now we're just going to clean this up a little bit, get rid of negative exponents and so forth. So our derivative is dy dx is equal to, now notice we have 1/2 x to the negative 1/2. So we're going to move that x to the negative 1/2 to the denominator. So we'll have 2 from the 1/2, and then we'll have a square root of x, or an x to the 1/2, either way, in our denominator. And that will leave this cosine of x to the 1/2. We could think of that as being over a 1, so that belongs in the numerator. So cosine of x to the 1/2. Plus, now moving on to our second term, again, we have a 2 in the denominator, and we have this negative 1/2 exponent. So this sine of x to the negative 1/2 power will also move to the denominator. So we will have 2 times sine of x to the 1/2 power, or you could write square root of x. And we can think of this cosine of x as being over 1, so it remains in the numerator. And at this point, there's really not a lot of other simplification that can be done, so that's a perfectly fine representation of the derivative. If you wish, though, you could take those 1/2 powers and rewrite them in square root form. So you could also write this as cosine of square root of x over 2 times the square root of x plus cosine of x over 2 times the square root of sine of x. Either one of those should be perfectly fine. So here's our third example. We want to find the derivative of f of t equals e to the 3t times tangent of 2t plus 1. So in addition to using the chain rule, we will need to be using the product rule because we have an exponential function being multiplied by a trigonometric function. So let's go ahead and get started. So we want to find f prime of t. That means we want, by the product rule, the derivative with respect to t of our first factor times our second factor plus the derivative with respect to t of the second factor times the first factor. So in essence, we're taking the derivative with respect to t of e to the 3t, multiplying that by tangent of 2t plus 1, then adding the derivative with respect to t of tangent of 2t plus 1 times the exponential e to the 3t. Okay, so we're basically done with the product rule at this point, and what remains is to find the derivative of the e to the 3t and the derivative of tangent of 2t plus 1, and then see what we end up with. So f prime of t equals, now by the chain rule, the derivative of an exponential function is an exponential, but we have an argument here of 3t. So when we apply the derivative, we're going to have e to leave my argument alone, or keep my argument, times the derivative of my argument. Again, that's the rule for exponential functions. The derivative with respect to x of e to the x is e to the x. So the derivative of e to the 3t is e to the 3t, but we have to attend to the fact that we do have this argument of 3t and must apply the chain rule. Hence, the derivative with respect to t of 3t. Now we're going to go ahead and multiply that by tangent of 2t plus 1 plus, and now we have our tangent function we need to take the derivative of, and our tangent function has that argument of 2t plus 1. So we'll need to use the chain rule. So the derivative of the tangent function is secant squared. So I'm going to have secant squared of, and we leave our argument alone, then we multiply by the derivative with respect to t of our argument. And our argument that we were leaving alone in our secant squared is 2t plus 1. So there's our chain rule times the exponential e to the 3t. All right, so then we have f prime of t is equal to, now the derivative with respect to t of 3t is simply 3. So let's write this as 3e to the 3t. So I am choosing to write this derivative in front of my exponential. So 3e to the 3t times tangent of 2t plus 1 plus, let's see, we have secant squared of 2t plus 1 times my derivative of 2t plus 1. The derivative of 2t is 2, and the derivative of 1 is 0. So this is in essence 2 plus 0. So 2, I can go ahead and write plus 0. You don't have to, but you can. And then times our exponential function, e to the 3t. So just cleaning up that second term just a little bit, f prime of t equals 3e to the 3t times tangent of 2t plus 1 plus, and then I'm going to go ahead and write this constant 2 first, more like a coefficient, and we have 2 secant squared of 2t plus 1 times e to the 3t. I hope you find this helpful.